All right, so OTTER is very happy to have Kari Eifler speaking to us today from Texas A&M. She's going to talk about quantum symmetries of quantum metric spaces. So take it away.
Awesome. Thank you. Thank you so much for the introduction. This is great. OTTER has been very nice this last year, and I've really enjoyed it. So yeah, I'm going to be talking about quantum symmetries of quantum metric spaces. This is kind of the bulk of my dissertation that I'm finishing up now at Texas A&M. I work with Michael Brennan, so I'm kind of in this operator algebra / quantum information theory / quantum, or a whole bunch of other fields kind of all meshed together. So feel free to ask questions. I cannot see the chat nor your faces, so you'll have to unmute yourself and let me know if there are questions, but please feel free to interrupt me. The outline of the talk today, I'm going to be talking, I'll start off with compact quantum groups, where I'm going to use a lot of intuition and motivation, and then we'll eventually get to the definition, which won't matter as much as really making sure that the intuition is there. And I'll give an example of a compact quantum group Sn+, and that'll kind of be the main example that we'll use to get other examples later on. I'll then get into what quantum metric spaces are, and just have the definition and look at some quantum symmetries of quantum metric spaces. So that'll kind of be where the title comes into play. And then finishing off with non-local games. They're really fun, very intuitive, and I'll connect the non-local game theory back to the more operator algebra area up here. And so that's the plan. Hopefully there'll be lots of examples along the way to give a lot more intuition. And another thing that I want to say, whenever I say quantum, it's kind of just a fancy way to say non-commutative. So I'm saying quantum a whole lot. Really what you should be thinking is non-commutative, just faster to say quantum. So starting off with compact quantum groups. So quantum groups, these are going to be used as a term to describe a special class of Hopf algebras. They've been studied a whole lot, and their representation theory is really important. So they're used in operator algebras, operator theory, quantum information theory, as well as in representation theory and knot theory and topological quantum field theory, and probably a whole bunch of other areas that I'm blanking on at the moment. And the idea behind it, so really to get that intuition, is, so we know from Gelfand theory that every commutative unital C-star algebra is going to be isomorphic to C of X for some compact Hausdorff space X. So rather than looking at our commutative C-star algebra, we can just look at this function algebra here. And moreover, we also know that every unital star homomorphism from C of X to C of Y, this is going to be of this form. So F gets mapped to this map in C of Y, which is defined by this unique continuous map phi from Y to X. So basically what Gelfand duality says, summing that all up, is that all of the important information about compact Hausdorff spaces is captured by the theory of commutative C-star algebras. So the key here being commutative. I think I say that again on the next slide. Yeah, function algebras of compact spaces, that is just directly correlated to commutative unital C-star algebras. And I keep on saying that quantum means non-commutative, so you can kind of guess where we're going. So the function algebras of quantum spaces, this is then related to non-commutative C-star algebras. And I'm not really going to define what a quantum space is, just think of this as being the analog of non-commutative C-star algebras. Now, we also know from Gelfand duality that if I want to go from a compact space to now a compact group, I can do this entirely by looking at extra structure on this commutative unital C-star algebra of functions, C of G. And so to go from a quantum space to a quantum group, I'm just going to put that exact same extra structure on an arbitrary, possibly non-commutative unital C-star algebra. So that's hopefully all of the intuition behind it. And I keep on saying that we're going to look at C of G, where G is going to be a compact group. So let's go ahead and do that, and we'll kind of see more how this Hopf star algebra comes up. And this will hopefully now, that was the intuition, hopefully now this is the motivation for the more technical definition that we're getting into. So if we take a compact group G, we're going to look at the function algebra C of G, and we can consider this homomorphism here. This is delta, it goes from C of G into C of G times G, and it maps here. So you can see that the group action is represented here by this delta, or is captured by this delta. And this delta, you can go through and check that it satisfies this, this equation right here. It looks a little bit strange why I'm saying this, but you'll see in a second. I'm going to use this equation again later. We also know that there's this natural isomorphism. I just want to point it out from C of G cross G into C of G tensor C of G. And that's just given by the one that you think it should be. So you take the tensor product and that just goes to the product on G of H. So just to make sure we know that there's this isomorphism. Now we also have a map epsilon. It goes from C of G into the complex numbers, which just takes F and maps it to F of the identity. And that's going to be this identity map. And the unit condition of the group, so just E times G is equal to G, that is going to translate. We can write it now in terms of this map. And it says that epsilon tensor identity composed with this delta up here, that's going to equal the identity. And if you go through and write it out, you see that that just is the exact same as the unit conditions on the group. Now, the other thing a group always has is inverses. So we're going to have a map that represents that. So we have S, it goes from C of G into C of G, and it takes F of G and maps it to F of G inverse. And the inverse conditions are going to translate to this funky equation here, which looks really complicated. It looks way more difficult than just saying G times G inverse equals the identity, but it captures the exact same information. And again, if you go through and write it all out, you're just going to get back to that same G times G inverse equals E, and vice versa if you go G inverse times G. Here, M is going to be the multiplication map. It just takes M of F and G to be F of G times, sorry, M of F at G. There should be an H here too. It goes to F of G times H. And we've got this unit map here, which just sends 1 to the identity. But yeah, so we've got these three equations that are satisfied by these three maps. So this equation for delta, this equation for epsilon, and this equation for S, that inverse map. And so how we're going to define a hop star algebra is we're going to say it's a unital star algebra A, and together we're going to have these homomorphisms. So we're going to have delta from A into A tensor A, satisfying, this is the exact same equation from the previous slide. I wish I was not giving a slide talk because then you would see that these are the exact same equations. So you'll just have to trust me. Epsilon here is going to satisfy this same equation from before, and S is going to satisfy this equation here, which is the exact same as before. That hopefully tells you where these equations are coming from, is it really comes from that example C of G. Now, if I go back to that example, we can see that this co-multiplication operator, that's what I'm going to call that delta, it captures the operation of the group here. And we want to know, what does that look like in the non-commutative case? Well, that's where we're going to get compact quantum groups. So Warnowick's said that a compact quantum group, this is going to be a unital C star algebra A equipped with a unital star homomorphisms. They're going to be called co-multiplication, and it takes delta from A into A tensor A, such that we want this first equation to hold. Delta tensor identity composed with delta, you can switch that identity and delta. That's going to be called co-associativity. And we also want these two spaces here, the span of A tensor 1 times delta of B, where A and B are just some elements in our C star algebra. We want this to be dense in A tensor A. And the same if we switch that 1 in the A, we still want that to be dense. And that's going to be called the cancellation property. So this time I was smarter. I put that up at the top so hopefully we can remember it. And if we go back to that one example, we're going to take G being a compact group, A to be the function algebra on G. We want to say that this is a compact quantum group and make sure that that's true. And we're going to need a co-multiplication given by it. So here we're going to take delta from C of G into C of G tensor G, and it's going to map F of G times H into F of G group multiplication here times H. And we actually know that this is going to be the only commutative compact quantum group. So any single compact quantum group with that definition from Warnowick's, which satisfies those three, has three homomorphisms that satisfy those three identities. If A is commutative, then the compact quantum group is just going to be C of G for some compact group G. So this is an example of a compact quantum group, but it's actually the only commutative example of a compact quantum group, where, remember, non-commutative essentially is where the quantum is coming into play here. So that is the definition of a compact quantum group. And then I'll go into an example next to hopefully make everything make a little bit more sense. So the symmetries of a structure X, we should know what these are, and they're just going to be viewed as any of the transformations of X which preserve its relevant properties. So depending on what X is, certain properties will be preserved. In the case of a metric space, the thing that we care about is the metric. And so we're going to say the symmetries of a metric space are going to be all of the transformations that don't change the metric. And those we just call isometries. And so we're going to call the isometry group. You can think of this as being the classical symmetry group of a metric space. This is the group of all of the bijective isometries from X onto itself. And the group operation here is function composition. There's a lot of natural properties that come up. They can be composed in an associative manner. There's going to be a trivial symmetry, and each symmetry here is going to admit an inverse symmetry. So that is classical symmetries that we are familiar with. I now want to look at what's called quantum symmetries. So before that, I need a definition. We've got a magic unitary matrix. It's going to be a n by n matrix over some star algebra A, where each of the entries are in that star algebra, and we want it to satisfy two conditions. The first is that each entry looks like a projection, so uxy equals uxy squared equals uxy star. And the second is that we want the sum over every row to be equal to 1, and the sum of, I should say it this way, the sum over every row to be equal to 1, and the sum over every column to also be equal to 1. And where this comes in with the symmetry language is if we take this star algebra to just be the complex numbers, so the easiest star algebra you can think of, then what this definition just looks like is it says that our matrix U, our magic unitary matrix U, that's going to be an n by n matrix with complex entries. That just looks exactly like a permutation matrix. This first criteria says that each entry is just 0 or 1, and we want the sum over every row to be 1, sum over every column to be 1. So that just says there's a single 1 in every row, a single 1 in every column. And we end up getting permutation matrices. But this is now a way to look at you can think of it as permutation matrices over other star algebras that are maybe more complex than just the complex numbers. Now we know what Sn is. This is just the symmetry group on n points with no additional structure, but we can write this in a different way. So if we look at the function algebra on Sn, this is actually going to be isomorphic to the universal C-star algebra generated by the entries of an n by n magic unitary matrix, with the additional constraint that each of the entries commute with each other. And so yeah, that just gives you the symmetry group of a finite set with no extra structure. But if we now try to consider the quantum symmetry group, then you probably can see where the definition is going. We're going to define the compact quantum group Sn plus by the universal C-star algebra generated by the entries of an n by n magic unitary matrix, where it looks exactly the same, except I've now dropped this criteria that the uxy have to commute. And that's how I get this quantum, or non-commutative, symmetry group of a finite set, again, just n points with no extra structure. If I move that up, I said it's a compact quantum group here, but then we need to know what the co-multiplication is. And in that case, it's going to be defined as like this. So delta of uij goes to the sum of uik tensor ukj. A natural question to ask is, well, does this matter? Is the quantum symmetry group any different than the classical symmetry group? And the answer is yes, in some cases. Maybe I should have said the answer is no for n being 1, 2, or 3. Those two groups look exactly the same. We don't get anything by dropping that non-commutative criteria. But we do get something new if we take n large enough. So for any n greater than or equal to 4, there's a lot of symmetry that we get in the quantum case that we don't get, that's not captured using classical group theory here. So what this says is that even classical objects, as you might think as boring as just 4 points, no extra structure, they have a lot more going on if we consider quantum symmetries rather than just classical symmetries. So this kind of motivates why I look at very simple objects, but from a more complicated point of view by using those quantum symmetries. As well, the reason behind this is really easy to see why these aren't equal. Wang showed that you can take any pair of projections, P and Q in B of H, and consider this matrix here. This is going to be a magic unitary matrix. You can see that the sum of every row and every row goes this way, and every column is just going to equal 1. And you can see that each entry is, of course, a projection. But the entries don't have to commute. You could pick P and Q in a clever way so that they don't commute. So that's the example. For n greater than or strictly greater than 4, just pad this with a whole bunch of 1s down here, and you've still got a good example. And so this compact quantum group Sn plus is really going to be the basis. You can think of this as the quantum analog of Sn, of course, but it's going to give us a lot of the quantum symmetries for other items, not just endpoints with no extra structure. And we'll see that in a bit. So that's an introduction, hopefully, to compact quantum groups. Now moving on to quantum metric spaces. So again, quantum here just means non-commutative. Before I get into it, I want to kind of remember, what is a finite metric space? So it satisfies these 3 axioms. We know and love them. But another way that we can look at a metric space, rather than looking at these 3 axioms, we can instead consider this family of relations. So we say that x is related to y if the distance between x and y is less than or equal to t. And then we can recast these axioms as these 3 properties. So the distance from x to y being 0 if and only if x equals y. This is the same as saying that R0 is the diagonal relation. So in R0, x is only related to x. And if x is related to x, then it is in R0. Saying that the distance from x to y is the same as the distance from y to x, we can recast this as saying RT is equal to the transpose. So if x is related to y inside of RT, then y is also related to x inside of RT. And the triangle inequality here, we can recast this as saying RS times RT is contained in RS plus T. So if x is related to y inside of RS and y is related to z inside of RT, then x is related to z inside of RS plus T. And so that hopefully is going to justify the next definition. So what we call a quantum metric space, there's a number of different definitions floating out there, and they're in some ways equivalent, in some ways not. But the one that I'm going to look at is the definition of Kupperberg and Weaver. And they define a quantum metric space to be a von Neumann algebra M. Let's set that inside of some B of H. And it's going to be a 1-parameter family of weak star closed operator systems. So this just means that we've got the identity and it's going to be self-adjoint. And we're going to call that family, each family for a T, VT, sitting inside of B of H. And we want a few properties to hold. So the first is that Vs times Vt is contained in Vs plus T. You'll see that that looks pretty close to this criteria here. We want that Vt is equal to the intersection over all s greater than T of Vs. And if you replace these Vt's by the Rt's, you can see that this property also holds for these relations up here. Finally, we want V0 to equal the commutant of M inside of B of H. And we can see that these criteria here, the 3 axioms of a metric space, correspond to, we can now recast that in terms of this 1-parameter family. So that last criteria looks the same. The fact that each VT is an operator system, that says that it's self-adjoint. So we get this recasting here. And again, it being and we said that V0 is equal to the commutant of M. Of course, the identity is in the commutant, so the identity has to be inside of V0. And that looks the same as saying that R0 is the diagonal relation. But the second one, you can see that that is still true for the relations RT, and so that's where that sneaks in there. The rough intuition here is that each of these VTs is going to consist of operators that don't displace any mass by more than T units away from where it started. So VT can't move anything more than T units. I'm going to throw the 3 criteria up here again, just to kind of keep that in the front of our minds. And let's look at the classical case. I'm calling this a quantum metric space. That means it should expand or extend the definition of a classical metric space. So we're going to start off with just a classical finite metric space. I'm always going to consider finite objects for this talk. And we can consider the von Neumann algebra M to be L infinity of X. This is going to be all of our bounded multiplication operators on our Hilbert space L2 of X, where here we're taking our Hilbert space to have a standard orthonormal basis. Just as a reminder, what bounded multiplication operators mean, for every f inside of our von Neumann algebra, it acts as the multiplication operator on f of f on g at x is f of x times g of x. And how we're going to define our parameters is we're going to say that VT related to this classical metric space X, this is going to be all operators A inside of B of H, such that the inner product of A times EY inner producted with EX is equal to 0 if that distance is too big. And since we're dealing just with finite dimension or finite metric spaces, then we can also say that this is equal to the span of the rank 1 operators VXY, which map G into this inner product here times EY, such that the distance from X to Y is less than or equal to T. And these are just equivalent definitions. And this is going to give us a quantum metric space in the sense of Kupperberg and Weaver. I don't remember. Yes, I do. Go through the proof. So the first thing we want to know is that M is equal to M commutant. That tells us that M is going to be a von Neumann algebra. And that's true. You can check that this M is a von Neumann algebra. It's going to be a commutative von Neumann algebra, and it's in fact the only kind of commutative von Neumann algebras. The first criteria here, we want Vs times Vt to be contained in Vs plus T. And you can check that. So for the rank 1 operators, if Vxy is in Vs and Vzw is in Vt, then when you take that product, you end up looking at that is going to equal 0 if y doesn't equal z. And then if y does equal z, then we end up with Vxw. And that does sit inside of Vs plus t. You can check that since the distance is going to be less than that sum. For the second criteria, we want that Vt is equal to the intersection of the Vs's for all s greater than t. Since the Vt's are going to be nested from that first criteria, we know they're nested. And so we can say that Vt is going to be contained in each of those Vs's where s is bigger than t. So it has to be contained in that intersection. Going the other way, if we have some rank 1 operator inside of Vs, and that's going to be in Vs for all s greater than t, then we know that this distance has to be less than or equal to t. And so Vxy is going to also be contained in Vt, making those two sets equal. And finally, we want V0 to equal the commutant of M. And that's true. We can see that it's equal to the span of Vxx, so those diagonal operators in B of H. And conversely, if we take anything in the commutant, so any Vxx, then we can always define f of z to be delta of, at that point, x. That's going to be an L infinity of x. And so this diagonal operator Vxx is going to be the multiplication operator, which does sit inside of M. Okay, so that hopefully justifies that this is indeed going to be a quantum metric space. But this is actually going to be all of the quantum metric spaces. So if Vt is we can get from quantum metric spaces back to classical metric spaces. So if Vt is a quantum metric on some L infinity of x, then we can get back to a classical metric space on x by defining the distance from x to y to be the infimum of all t's where there exists an a and Vt such that this inner product is non-zero. Kind of a mouthful, but the main idea is that you can get from classical metric spaces into quantum metric spaces. And in the case that you're looking at a quantum metric space on a commutative von Neumann algebra, so on L infinity of x for some x, then you can go the other way too and get back to a classical metric space there. Okay, so now getting back into isometries and quantum symmetries. So Banica, he took a classical finite metric space, call it XD, where D here is going to be the n by n distance matrix. And he defined a quantum isometry group. So isometry in this case just means a quantum symmetry group for a finite metric space. He defined that isometry, the quantum isometry group, to be the function algebra on Sn plus. So remember, that is the quantum symmetry group on endpoints with no extra structure. And now we're going to add that extra structure from the metric space by quotienting out by the ideal generated by UD equals DU, where remember D here is the distance matrix and U is going to be our magic unitary matrix that generates C of Sn plus. In the case that I was just looking in the totally classical case, and I'm looking at the classical symmetry group of a classical metric space, this would look the exact same. I would just drop that plus here. So he really just added that plus, and that now brings us into quantum, the quantum world. And our goal that we have is that we want to capture Banica's definition here, By using now, instead of classical metric spaces, we want to expand that into the Kupperberg-Weaver quantum metric spaces. And so the definition we have, I want to warn you in advance, it's kind of long and gross. I will hopefully justify where it comes from as we go through. So we're going to consider two quantum metric spaces, M1VT and M2WT. That's going to have fixed orthonormal bases. So because we're in the finite dimensional case, I'm always considering finite dimensional. M1, we can look at this as being the vector space sitting inside of the Hilbert space. And so we're considering, this is kind of bad notation, an orthonormal basis EJ of M1. But you can think of your von Neumann algebra as being a vector space. And we're going to define the quantum isometry group between quantum metric spaces, between these two quantum metric spaces. This is going to be the universal compact quantum group generated by a matrix P with entries Pij. That's going to sit inside of this tensor product here. And we want that P to be such that this map here is a unidal star homomorphism. And I know this looks gross, but the idea is that when we restrict down to the classical case, what this says, this is just a fancy way to say that P is a magic unitary matrix. So a magic unitary matrix, we know and we love them, and they describe all of the quantum symmetries. That is the idea of this part of the definition. Second, we also want to ensure that the conjugation map here, so it maps T into the conjugation by this, in the classical case, a magic unitary matrix P. We want these to leave VT invariant. So saying that alpha VW of VT should sit inside of WT, tensor our universal compact quantum group. And we want that to be true for all T. In the classical case, this just says that distances can't grow under the diagonal action of the automorphism group. And that's something that we see is true for classical symmetry groups of classical metric spaces. So that's where that definition comes from. It's very long and gross, but the nice thing is that if we take a classical finite metric space, so we're starting off with a classical finite metric space, and then we take that quantum metric space that corresponds to it that I had defined before. So we take our von Neumann algebra to be L infinity of X, Hilbert space is L2 of X, and we're going to take these VT to be that standard construction that I had mentioned before, so the span of those rank 1 operators. Then what we end up getting is that Banica's quantum symmetry group of the classical metric space lines up with this new definition of a quantum symmetry group of quantum metric spaces for those quantum metric spaces that correspond there. That was a whole mouthful, sorry. The nice thing is that we've now expanded it in an appropriate way that it lines up in the classical case, which is good. Now I'm going to shift over to non-local games. So if you didn't like those really long definitions, this is a little bit funner and more intuitive. So a non-local game is going to be played by two players, Alice and Bob. They come up with a strategy ahead of time. They are working cooperatively together to win against the referee. So you can think of Alice and Bob, they go to their bookshelf, they pull out a board game, their favorite board game, and they read through all of the rules that they have. They know the rules back, they read that rule book from the front to the back, and they know it off the top of their head. They're like, here's the strategy we're going to use in order to win. But as soon as gameplay starts, Alice and Bob can't communicate anymore. They can only rely on that strategy that they came up with before. And what one round of the game is going to look like, we're going to have the referee. We could be the referee. So let's say we are the referee. We give Alice a certain question, say it's question V, and we give Bob a certain question, say question W. Now remember, Alice and Bob can't communicate. They have no idea what question the other player got. But without communicating, they must reply with their answers A and B, and they only rely on that strategy that they came up with ahead of time. Finally, then the referee, he knows everything that's happening, and they're going to determine if Alice and Bob win that round. So knowing what V, W, A, and B are, they can check the rule book. They say, yes, you won. No, you didn't. If Alice had known what Bob received as a question and answered, she could also have checked the rule book and checked if they won or not. There's nothing really special about the referee in this case. And the goal is exactly what you would think the goal is. It's that they want to win every round of the game. So repeat this process over and over and over, and they always want to win. Okay, so I can make this a little bit more formal now. So let's say a synchronous non-local game. This is going to be given by this tuple of I, O, and lambda. The set I is going to represent the inputs or the questions that the players Alice and Bob can receive. And the set O is going to represent the outputs or the answers that Alice and Bob can produce. It's called Synchronous. This is a special class of games. I could drop that. I'm going to keep it in just because that simplifies everything. But so here it's important to note that if Alice could receive a certain question, so can Bob, because they share the same question set and they also share the same output set. Now the rules of the game, these are going to be represented by this function lambda, and it goes from the inputs, across the inputs, across the outputs, into just 0, 1. They're going to win the game if lambda of this tuple VW AB is equal to 1, and they lose if lambda of that tuple is equal to 0. The reason it's called a non-local game is because Alice and Bob can't communicate. So you can think of them as being in just separate offices side by side, but there's a really thick wall and they can't communicate. Or you can think of them as being very, very far away, many light years away, so that communication just isn't realistic. And we also have the final condition that every game has to satisfy. If the input for Alice is V and the input for Bob is V, then the only way that they might win is if their two outputs are the same. So if they receive the same question, their answer also has to be the same. It basically says that the referee, or that they can't contradict each other within a certain round. But between rounds, they can change their answer. So you think of it, the referee's memory gets wiped every round. He can't remember what happened last round. He just goes with, okay, I've currently given Alice and Bob the same question, and they have responded with the same answer. Or they have not responded with the same answer, and they immediately lose. And so that's going to be a synchronous non-local game. There's a number of different strategies that Alice and Bob could come up with. The first is going to be called a deterministic strategy. And so this is just going to be a single function h from the inputs to the outputs, such that if Alice or Bob, say, receives input v, then they're going to answer with just h of v. So it doesn't require any thinking. They say, here's our strategy. It's just this map. If I receive this, plug it into my function, and I'm just going to answer whatever that tells me. Now you could also have a random strategy. And so a random strategy comes into play if during different rounds of the game, Alice and Bob receive certain inputs, but they answer different, they have different responses to the same question between rounds. So that's going to be called random for obvious reasons. As the outsider, or we can think of ourselves as the referee or as just an outsider observing this game, what we can do is we can end up getting these conditional probabilities that given that the questions were V and W, what's the probability that the answers are A and B? We're going to watch those. Of course, those probabilities are between 0 and 1. We can also see that the sum over all of the A and B's is equal to 1. Since if you set certain inputs to be V and W, well, then the probability that they respond with something is equal to 1. We're going to call a strategy perfect if lambda of VW AB equals 0. So if they lose with that tuple, then the probability of them giving that answer is 0. You can also think of this as they win with probability of 1. I don't know why the literature doesn't just say that. But yeah, that is when a strategy is perfect. And so I'm really concerned about whether there exists a perfect strategy or a non-perfect, or there doesn't exist a perfect strategy. Other people look more at the percent of the time that you win. And yeah, I just care, is there a perfect strategy or is there not? So now looking at a specific game, we can look at what's called the metric isometry game. If you've heard of the graph isomorphism game, this is a generalization of that. So we're going to start off with two classical metric spaces. The inputs and the outputs are going to be the same set, and it's going to be the disjoint union of x and y. That disjoint union just means that if Alice gets a certain point from x, she at least knows it's from x because we're taking the disjoint union. Now the rule function is going to satisfy that lambda of the input for Alice, the input for Bob, the output for Alice, the output for Bob, they are going to win if the following conditions are met. The first is that XA and YA belong to different spaces. So if Alice receives an input from X, her answer has to be from the other space, so from Y. And ditto for Bob. So if Bob receives a point from Y, he has to respond with a point from X. Now, if the inputs for Alice and Bob are from the same space, then the distance between the two points that Alice and Bob receive as questions has to be equal to the distance between the 2 points that they answer. This in particular tells us that the game is synchronous. So we see immediately the inputs and the outputs are equal, but we can also see then if the referee were to give the same point to both of them, that means the distance between the 2 points is 0 because they gave them the same points. And so therefore the distance between the answers that they give has to be 0. From a metric space, we know that those 2 points then have to be equal to each other. So this says that they can't contradict in a single round. Now, finally, what we want is that if XA and XB are from different spaces, then we want that XA equals YB if and only if XB equals YA. This looks a little bit strange. So these first 3 criteria are essentially saying that there's some map, there's an isometry from X to Y, and there's another isometry from Y to X. And we want a single isometry that's bijective. So we want those to be inverses of each other. And this last criteria says that. And what we can see is that there's going to exist a perfect classical strategy or a strategy that you can use in the real world if and only if X is isometric to Y. And here I'm kind of slipping it under the rug, bijectively isometric. That's pretty easy to see. If X and Y are isometric, then of course you can come up with this bijective map, and you can just answer. That can be the deterministic strategy that you use. So you just use that map to determine what you should answer. Going the other way, excuse me. Going the other way is a little bit more complicated, but not too much. And we'll see that in a second. So now I've used the word quantum strategy, but now I'll define that. And a classical strategy for non-local game is one in which the only resource available to the players is some sort of a shared randomness. Or you can think of it as Alice and Bob have a shared probability space. Now, the physicists describe it as Alice and Bob are in their office. There's a window that they're able to hear from the outside, and there's an oracle sitting outside chanting numbers. And if the oracle chants 0, then they're going to go with predetermined strategy 0. If the oracle chants 1, they go with predetermined strategy 1. So there's this shared randomness that potentially could help them out in the game. Now, in a quantum strategy, the players are allowed to perform local quantum measurements on a shared entangled space. So what's really nice about non-local games is they provide us a way to certify quantum behavior through the observation of only classical data. So we're in the real world, we're only observing classical data with these conditional probabilities, but we can see that sometimes they win in times that they shouldn't. So if there's no winning classical strategy, but they're still able to win, then we know that there's some quantum strategy happening. And when they use quantum strategy, I want to emphasize it doesn't allow them to communicate directly, but it does allow them to correlate their answers in a way that they wouldn't be able to classically. With these probabilities, you can think of it as Alice is going to conduct a certain experiment in her lab, and Bob conducts a certain experiment in his lab. Depending on the outcome of those experiments, then that changes what they might answer. And there's a lot of different mathematical models that we can use to describe these conditional probabilities that arise. So we're going to let CT and K, this is going to be the set of the conditional probabilities that arise in model T. So we've got our classical models, our classical conditional probabilities, and we've also got our quantum commuting probabilities here. There's a whole bunch of other probabilities that lie in here, or different mathematical models, such as quantum tensor and just quantum, quantum spatial. There's some other ones that I'm blanking on, but I'm just going to focus on these 2 models. So just putting that up at the top. So in classical, I kind of said what that is, but to write it more formally, so remember it means that Alice and Bob can just have some shared randomness or a shared probability space. And so if they share this probability space here, and each is going to have random variables. So Alice has random variable FW, F omega A. Bob has his random variable. And the probability that they give the answers AB to the questions VW, that's just the probability that the omega that they choose from the conditional or from the probability space gives them that answer with that input. So if Alice gets question V, what's the probability she gives A? That depends on the probability that that omega that the oracle is chanting lines up there. And same with Bob. Now, in the case of quantum commuting, there's going to be a Hilbert space H on which Alice and Bob are allowed to make measurements. And they're going to have a shared state psi. Alice also is going to have orthogonal projections, EVA in B of H, and they're going to satisfy that the sum over all of the outputs is equal to the identity. Bob has the same thing. He also has orthogonal projections that satisfy the sum over all the outputs equals the identity. And I definitely forgot to, I made a little typo. We should also include that the EVAs and the FWBs are going to commute, hence the name quantum commuting. So yeah, we needed the orthogonal projections to commute. But all of the conditional probabilities that arise are going to come of this form. So they're going to be the inner product of Alice's experiment, Bob's experiment, times that shared state inner producted with the shared state again. And so that's quantum commuting. That's going to sit inside of the classical case, since if we took the Hilbert space to just be the complex numbers, we'd get back down to this case. Now, rather than looking at the game itself, we can instead define an algebra that we're going to study. So we're going to define the star algebra of a synchronous game G. This is going to be defined as the quotient of the free star algebra generated by EVA, which is subject to these relations. So each EVA looks like a projection. We want the sum over all of the outputs to be equal to EVA. And we want that EVA times EWB is equal to 0 for all V and W, VWAB, where they lose that round. And what this does is this encodes the algebraic structure of the game. So all of these conditions are going to be forced upon us by the restrictions of a winning output that Alice and Bob give. And the motivation here is that the representation theory of this star algebra is going to determine whether or not perfect strategies exist. You can think of this as also being a non-commutative analog of the space of isometries from X to Y. And I also want to say that it might be the case that once we take the quotient by these relations, we might just end up with 0. That's very possible to happen. Nothing's saying that that can't happen. So yeah, I said the representation theory of this star algebra is going to tell us when certain strategies, perfect strategies exist. And that's true. So G is going to have a perfect deterministic strategy if and only if G has a perfect classical strategy. So I think that's pretty wild. With this class of games, if there is a perfect strategy, classical strategy, then there immediately exists a perfect deterministic strategy. So what this says is that oracle sitting outside chanting or having that shared probability space doesn't help them win at all. They could just have made a map at the beginning and said, here's our strategy. This is the deterministic strategy we're using, rather than having any randomness. This is also going to be true. So there's a perfect classical strategy if and only if there exists a unital star homomorphism from our game star algebra into the complex numbers. So rather than looking at the game itself and seeing if we can come up with a deterministic strategy, we can look at that game star algebra and look at the representation theory of it. G also has a perfect quantum commuting strategy if and only if there exists a unital C star algebra with faithful trace and a unital star homomorphism from A of G into that C star algebra with faithful trace. So I said, we've got this game star algebra. Maybe we should look at what it looks like for a certain game. So if we consider that metric isometry game, then what the game star algebra is going to look like for that metric isometry game, it's going to be generated by EXYs. So here we can reduce it down to the case that X is in X and Y is in Y, rather than just being in the inputs and the outputs. And it's going to be subject to the relations that this U, which has entries EXY, that this is a magic unitary matrix. So remember, each entry is a projection. That comes from the game star algebra criteria that each entry looks like a projection. And we also want the sum over every row to be equal to 1 and the sum over every column to be equal to 1. And we want this to be to have the case that one tensor, the distance matrix from X times U is equal to U times one tensor, the distance matrix from Y. Now, if we just take this in the classical case, then that This U, remember, a magic unitary matrix in the complex numbers, is that just looks like a permutation matrix. And so what we get here is that the two metric spaces have an isometry between them. There's a bijective isometry from X to Y. But yeah, now in the case of non-commutative or non-classical, when we're looking at those sorts of strategies, we can end up looking at what this game star algebra looks like, and we know exactly what it looks like. And so what we can find, excuse me, is that for two classical metric spaces, X and Y, we can again consider their corresponding quantum metric spaces that I had defined way at the beginning. So taking L infinity of X to be our von Neumann algebra, and taking these VTs to be that span of the rank 1 operators. Then what we end up finding is that, so this is the quantum symmetry group of quantum metric spaces. That is going to be the same as the game star algebra for the two metric spaces A and Y, or X and Y. And so rather than looking at the quantum symmetries, we can now look at it from the non-local game perspective and see what's going on here. In the case of the metric isometry game, there are certain games that can be won classically, that can be won using quantum strategies, that can't be won using classical strategies. The smallest example that we've got has 24 points in X and 24 points in Y, so it's very big and ugly, but we can show that those are exactly quantum isometric and not classically isometric. And finally, if we take two classical metric spaces, then the following are going to be equivalent. The first is that game star algebra is non-zero. So I said, if you take that quotient, it might be 0. In the case that it's not 0, that's exactly equivalent to saying that that admits a non-zero C-star representation, which happens if and only if the metric isometry game on X and Y has a perfect quantum commuting strategy. So that Hilbert space that they share, there's now a perfect strategy that comes into play here. And this isn't going to be true for all games. It's not even true for all synchronous games. The graph homomorphism game, if you've heard of it, is an example where this isn't true. But this is true for the metric isometry game. Awesome. Thank you.
Thanks, Kari.